So the first question that we were looking at involves buffer solutions. So it says, which of the following are buffer solutions? Assume equal molar concentrations of all solutions. And so just to kind of recap, buffer solutions include a weak conjugate acid, and its conjugate base. These are the criteria for a buffer solution. You need to have a weak conjugate acid and a weak conjugate base. And so what we're looking for, since they're equal molar concentrations, we're looking for the ones or the combinations that include a weak conjugate acid and its weak conjugate base. So we look at the first one. We have HCl and KOH. Well, HCl is not a weak acid. KOH is not a weak base. So this cannot be a buffer. Again, we're assuming equal molar concentrations. Next, we have HNO2, which is a weak acid. So check, that's a weak acid. And NO2 is its conjugate base. So that's a weak base. And so this one would form a buffer. And the reason you would want to make buffers with equal molar concentrations is because that'll give you the best buffer capacity for you to use. Next, we have HBr. We ask ourselves the question, is HBr a weak acid? The answer is no. And since there's equal molar concentrations, it doesn't matter what the conjugate base is, even if it is a weak conjugate base, which is what it is. Since they're equal molar concentrations and we have a strong acid, this would not be a buffer. Next, we have CH3NH3Cl and CH3NH2. So again, the acid is the cation. Remember, we talked about in our last session, acids can be either molecules or cations. So here, this cation is an acid. We ask the question, is this a strong acid? The answer is no. So that means it's a weak acid. And CH3NH2 is its conjugate base. So D would make a buffer solution. Next, we have HClO4 and KClO4. Now, HClO4, we ask the question, is it a weak acid? The answer is no. Perchloric acid is a strong acid. And even if we look at its conjugate base, ClO4 minus, it is not a weak base anyway. So this would not form a buffer. Again, we're assuming equal molar concentrations. Next, we have HF and LiOH. Is HF a weak acid? Yes, it is. Is LiOH its weak conjugate base? No, it isn't. So therefore, this would not form a buffer, again, because we're assuming equal molar concentrations. Next, we have C6H5COOH. Is this a weak acid? Yes, it is. Is C6H5COO its conjugate base? Yes, it is. And so this would be a buffer solution. So again, buffer solutions are made up of typically the weak conjugate acid and its corresponding conjugate base. Now, in this example, we assumed equal molar concentrations. So in this one, in this question, we want to determine which of the following are buffer solutions, but you'll notice here that we have different concentrations of the conjugate acid and conjugate base. Now, again, a buffer is made up of a weak conjugate acid and weak conjugate base. And typically, Well, I should say that back. Typically, it's a a buffer is made up of a weak acid and weak base. Generally, these include the weak conjugate acid and its corresponding conjugate base. However, there could be some occurrences where as long as you have a weak acid and a weak base, that would still form a buffer, but generally, when we're talking about buffers, we're talking about a weak acid and its corresponding conjugate base. Now, when we're given different concentrations of the weak acid or the conjugate acid and the base, or the acid and the base, the only following would form buffers. So let's say we have a weak acid and a strong base. We want to know if this forms a buffer solution. It only forms a buffer solution if the concentration of weak acid is greater than the strong base. So again, the general form for a weak acid is HA. The general form for a strong base is OH minus. So when you have a combination involving a weak acid and a strong base, as long as the concentration of weak acid is greater than the concentration of the strong base, then a buffer will form, because what will happen is the strong base will be converted into the weak acid's conjugate base. So that's one combination. Next, if we have a weak base and a strong acid, only forms a buffer if the conjugate base, aka the weak base, is greater concentration than H3O plus concentration. So as long as the concentration of weak base is greater than that of the strong acid, it will form a buffer. And what happens is the moles of strong acid get converted into the conjugate acid of the weak base. So you lose some moles of weak base to make the conjugate acid for that weak base. So now, knowing this, and again, if it's weak and weak, it doesn't matter the concentrations. So here we have a buffer made up of chlorous acid and sodium chloride solution. We want to know if this forms a buffer. Chlorous acid is a weak acid. Chlorite is its conjugate base. Yes, this would form a buffer solution. Next, we have ammonia and HCl. So ammonia is a weak base. HCl is a strong acid. So since we have this combination, we ask the question, is the concentration of weak base greater than the concentration of strong acid? The answer is no. So this would not form a buffer. Next, we have CH3NH2. This is a weak base. And we have 0.15 molar HI. This is the strong acid. So we ask the question, is the concentration of weak base greater than that of the strong acid? The answer is no. Next, we have C2H5COH. This is a weak acid. We have KOH. This is a strong base. And we ask the question, is the concentration of weak acid greater than the concentration of strong base? The answer is yes. So this would form a buffer. And this would form a buffer, just to let you know, this would form a buffer of the following concentrations. So what would happen is the KOH would react with the weak acid, and you would get a 0.05 molar weak acid with a 0.05 molar weak conjugate base. So this is the buffer that would result. Moving to E, we have a weak acid, HCl. We have a strong base, barium hydroxide. We ask the question, is the concentration of weak acid greater than that of the strong base? And at first glance, it may appear so. However, notice here that for every 1 mole of barium hydroxide, we have 2 moles of hydroxide. So 2 times 0.08 means we actually have 0.16 molar concentration of hydroxide. So therefore, since there's more strong base than weak acid, this would not form a buffer. Next, we have sodium bicarbonate and potassium carbonate. So sodium bicarbonate, bicarbonate is a weak acid, and carbonate is a weak base. So this would form a buffer. And lastly, we have potassium benzoate and sodium acetate. Potassium benzoate is a weak base, weak base. Sodium acetate, acetate is a weak base. So since you have 2 weak bases, this would not form a buffer. So again, for a buffer, we want a weak conjugate acid and its corresponding conjugate base. If there's a strong base present, the concentration of weak acid has to be greater than the strong base. If a strong acid is present, the concentration of weak base has to be greater than the concentration of strong acid to form a buffer. Okay. Now getting into calculating the pH of buffers. So here we have a buffer solution made up of 0.05 molar acetylsalicylic acid and 0.15 molar of potassium acetylsalicate. It's a tongue twister right there. And it gives us the Ka of acetylsalicylic acid. We want to know what's the pH of this buffer solution. So again, with buffer solutions, we're going to be using something called the Henderson-Hasselbalch equation, where the pH is equal to the pKa of the weak acid plus the log of its conjugate base concentration over its conjugate acid concentration. And so from this problem, we know the concentration of conjugate acid is 0.05. That of the conjugate base is 0.15. You may ask, well, how do I know the first one is the conjugate acid, the second one is the conjugate base? Well, the way I know is because we have COOH, so that H tells me it's acidic. And on the other one, we have COOK, which tells me that this is a conjugate base because we have a salt. And so now that we know the concentration of weak acid and weak base, we can find the pKa by taking the negative log of Ka. And since the concentration of weak base is greater than the concentration of weak acid, our pH should be greater than the pKa. So when we plug it in, we see that the pH is 3.92. So to calculate the pH of a buffer, this is what you do. You take the log of the ratio of the concentration of weak base over the concentration of weak acid added to the pKa. If the concentration of weak base is greater than weak acid, your pH will be above the pKa. If the concentration of weak acid is greater than weak base, your pH will be below the pKa. Now, a different take on calculating the buffer of the solution. Here we prepare a buffer by adding 0.35 grams of sodium hydroxide to 125 milliliters of 0.1 molar carbonic acid solution. What is the pH of the buffer? And it gives us the Ka of carbonic acid. So again, we're using the Henderson-Hasselbalch equation. Now in this one, we don't know the concentration of weak acid or weak base that makes up the buffer solution. But what we do know is the pKa. We can find that it's 6.35. Now to find the concentration of weak acid and weak base, we first have to find the moles of weak base we're starting with and the moles of hydroxide ions. And again, since it's hydroxide, it's going to react with the weak base. Excuse me, weak acid. So we're going to use weak acid to produce weak base. And again, we do this on the mole level. So initially, we have our moles of carbonic acid, our moles of hydroxide. We have no moles of bicarbonate. The change is all the hydroxide reacts with the carbonic acid to form bicarbonate. Now, if your moles of hydroxide exceed the moles of your weak acid, then this will not form a buffer because you've consumed all the weak acid. So again, the moles of hydroxide have to be less than the moles of weak acid for a buffer to form. Now we get our, you could say, equilibrium moles of both weak acid and weak base. We find the new molarity of the weak acid and weak base, and then we can calculate the pH. And it shouldn't be 7, that's a typo. I thought I fixed it. It should be 6.71. So that's the pH of this buffer solution. So again, whenever you're adding, a mass of strong base to a weak acid solution, this is the process you have to go through to determine the pH of the buffers, the resulting buffer solution. Okay, so I had a duplicate slide. So the last question, we want to know if we have a buffer solution made up of 0.15 molar HF and 0.08 molar potassium fluoride. And this makes up a total of 100 milliliters of solution. If 0.24 grams of sodium hydroxide is added to the buffer, what is the pH of the buffer solution? So before we begin that, let me just quickly show you how a buffer works. So we have a weak acid. So this is the equilibrium equation for a buffer solution. You have a conjugate acid and conjugate base. Now we have to reflect back to Le Chatelier's principle. So if we add a strong acid, what happens is if we're adding a product, say you're adding more strong acid, you're adding a product, it's going to shift to make more reactant, aka more weak acid, to establish or to reestablish equilibrium. So again, when you add strong acid, you're decreasing the amount of conjugate base, you're increasing the amount of weak acid to reestablish equilibrium. Likewise, if we add a strong base, so if we add a hydroxide, what happens is there's a secondary reaction. So as you add hydroxide, it reacts with the hydronium ion, so this decreases because you keep on producing or keeps reacting with the hydroxide that you added. So since this is decreasing, you're removing a product, so it's going to shift to make more product. And so as you shift to make more product, HA goes down, A minus goes up. So the concentration of weak base increases, the concentration of weak acid decreases. Because again, that hydroxide is removing the hydronium ion from that equation. You're decreasing the products. Le Chatelier's principle says it's going to make more product. So now with that in mind, since we're adding a strong base to the buffer, the concentration of F minus should go up. The concentration of HF should go down. So again, we're going to be using the Henderson-Hasselbalch equation. We need to determine the concentration of HF and F minus that remains after we add the 0.24 grams of sodium hydroxide. We can find the pKa by simply the negative log of the Ka. And we need to determine the initial number of moles of HF, F minus, and OH minus. And again, since we're adding a strong base, it's going to react with the weak acid to form more weak base. So initially we have this many moles of weak acid, strong base, and weak base. The change is all of the hydroxide reacts with the weak acid to form weak base. Now, just to let you know, if the moles of hydroxide are greater than the moles of weak acid, you've destroyed the buffer. So for example, if this said 0.02 moles of OH minus, then the buffer is destroyed. All we do is simply determine how much or how many moles of OH minus is left over, and then we can find the POH and pH. So again, if the moles of hydroxide exceed the moles of HF, the buffer is destroyed. So at equilibrium, we subtract 0.006 from the moles of weak acid. We add it to the moles of weak base. Now we can find the new concentrations of weak acid and weak base, plug it into Henderson-Hasselbalch, and we get a pH of 3.36. Now if we calculate the initial pH of the buffer, the pH equals 3.17 plus log of 0.08 divided by 0.15. If we did it correctly, when we added the sodium hydroxide, the pH should have increased. And we get that the original pH of this buffer solution was 2.9. So since we added that much sodium hydroxide, you see the pH of the buffer went from 2.9 to 3.36. And typically, the buffer range is plus or minus 1 of the pKa of your weak acid. So for this buffer, we can expect it to be between about 2.2 and 4.2. So in that would be the buffer range of this buffer. So again, if you take a strong base, it's going to react with the weak acid and make more conjugate base. If you react with a strong acid, it's going to react with the weak base to make more weak acid.